So, we are going to discuss the mean value theorems or mean value property. This is what I have mentioned there. So, mean value property is you will see soon, that is an equivalent property of harmonicity. Okay. So, let us begin with what is this mean value formula. Mean value formula. So, rather a theorem. So, let us make a start a theorem and then try to prove it. Theorem. So, you have your domain omega, that is there, and you have your let u belongs to C2 of omega be harmonic. That is Laplacian of u equal to 0 in omega. Then there are 3 components. So, let me compute. Then for any ball, you look at any ball of at the point. So, you choose a point y here, you look at a ball which is completely contained in omega, that means compactly embedded. There any ball of radius r centered at y, that means compactly contained in omega. It is not any for all bar, then any for we have u of y. Okay, let me do it in 3 steps. So, I do it a more general thing, be subharmonic. So, let me do it be subharmonic, that is Laplacian of u greater than or equal to 0. Okay. Last week, last lecture we have introduced this u is subharmonic if Laplacian of u had a, then you have the inequality less than or equal to is the nothing but 1 by n omega n r power n minus 1 integral over the boundary of the ball Br of y and then u of y, your ds of y, you see. So, ds of x. So, let me use the y is used here. So, let me use x here around that point. This is nothing but the surface area. So, this is nothing but the average 1 over modulus of dBr or integral of dBr of u ds, you see. So, this is the nothing but the average, surface average. This is nothing but surface average. This is 1. 2, if u is superharmonic, that equivalent to saying that minus u is subharmonic. So, you get the reverse inequality. Superharmonic, that is Laplacian of u less than or equal to, we get the reverse inequality. We get the reverse inequality. And the third one is if u is harmonic, you have it is both subharmonic and that is Laplacian of u equal to 0, then you have the equality. Okay. Then you have the, you get u of y is equal to the equality 1 by modulus of dBr into integral of dBr u ds. So, this is called the mean. In fact, you can also, this is all the, so let me go to the thing, you can also get, so let me write down that one. So, you can also get not only the surface average, you can also get u of y less than or equal to. So, you can also get the volume average, that means Br of y modulus integral of Br, okay, and u of x dx. So, you see, so you have both. So, this is the volume average. So, you have both the surface average thing. So, that is very interesting. So, if you want to find the value here at one point, you average. You can average it in anything, any ball, as long as the ball is inside. So, either you can take the surface average or you can take the internal average, surface average or the internal volume average. That is what you will be getting it, and that is true here also. This is also equal to 1 by B r of x modulus its average integral of Br of y. This is should be Br of Br of x only. Br of y modulus of Br of y into u of x dx. This is called the mean value property. It is also called mean value property. Mean value property. So, we will be using this. So, whenever any harmonic function satisfies the mean value property in every open ball, in that one. So, I am going to give a proof of this. Okay. So, let me try to give a proof of it. So, since the proof, so let me start the next page of the proof. Okay. So, use the divergence theorem first. Divergence theorem by. So, we are going to prove one, the other things we can deduce it. Divergence theorem. Divergence theorem tells you integral of Laplacian of u on any ball of radius, any internal ball. So, Br of y dx is equal to integral of the boundary Br of y du by d nu. This is a normal derivative with respect to ds. Okay. And you are given that Laplacian of u is subharmonic, that Laplacian of u greater than or equal to 0. So, this is less than or equal to 0, this quantity is there. Okay. So, I call this to be, say this is equal to, in fact I can define for any ball. So, if you have instead of r, I can define for any ball. So, you have a ball contained in omega, this is your y, I can take any ball. This formula is true for any ball of radius rho, because r I will reserve it for something else. Okay. So, I will integrate with respect to b rho, r also you can use it. Okay. So, this is true, and this depends on rho. So, I call this to be 0. So, this is my definition of g rho, and g rho is positive. So, I want to do something now. Write g rho is equal to, so I use this 0 integral of db rho of y du by d nu. I may not write each time d nu ds. Now, I want to take this derivative outside, but d by d nu depends on rho, because d by d nu is the normal derivative along this direction. This depends on rho. So, whenever you want to take a derivative outside whose integral is also depends on that variable, you cannot directly do it. So, one of the way you want to do it is that you translate to, you make it a integration, you try to make it in a fixed domain. Okay. So, whenever you have an integral which is varying with respect to a parameter, and if you want that derivative to take inside or outside, The one procedure is that you convert that integral to a fixed thing. So, now this is on x d6 of x. So, doing it. So, I want to translate to this to a fixed thing which is centered at the origin, and you want to translate this y here, and then the radius you want to make it. So, you have to make a dilation and translation. Okay. So, you make a change of variable, that is what you want to precisely do it. So, you make a change of variable x is equal to rho tau plus y. Then when tau varies from x varies from 0 to rho, in that ball this tau will vary from 0 to 1, you see it will vary. So, it will become a change of variable. So, this will become d b1 with respect to the 0, and then the normal derivatives, it will become d by d rho, because it is a normal derivative is rho here. So, get it du thing, and x is changed to y rho tau plus y. Keep it in mind, rho and y are fixed, only tau is now varying. So, the integration with respect to ds of tau. Okay. So, once this is there, now this is independent of the boundary integral, the surface you are integrating. So, you can take it outside, and then there will be a rho power n minus 1 here, because you are making a small rho. These things we have already seen it in our in fact we have seen it yesterday in the previous class. You will have, whenever you are changing a ball of a surface of radius rho to a radius 1, there will be a rho n power n minus 1 parameter coming. This variation we have seen it, and the integration is with respect to tau. So, that will become, so you will have rho n minus 1, and now I can take it d by d rho outside, and integral db1 0 into of u of y plus rho tau ds of tau, you see. Now, so I have achieved my thing. What I want is, of course, this is 0, and this is less than or equal to this. You have that condition. Now, look at here. So, I will go back by the same procedure after taking this derivative outside. So, now it is outside d by d rho. I can go back. When I go back, instead of while coming back, translating and dilating in this fashion, I got rho n minus 1. So, if I go back to the same ball, I get rho power 1 minus n, but that is within the derivative. So, I can go back in the same way. I get it p rho of y u of x ds of x. So, that is a kind of trick, you keep on using it, and this is positive, rho is positive. So, this implies this derivative, this is positive, because this is already positive, right. So, this implies that this quantity is positive. So, what do you do? So, that is a nice thing. So, now you integrate with respect to rho from rho 1 to rho 2, any 0 less than or equal to rho 1, less than or equal to rho 2, less than or equal to r. The ball r is fixed there. You can choose any rho 1 because this is valid, this formula is valid for any rho 1 and rho 2. So, if you integrate, this is, you can integrate. So, you will get, so the integral, you get exactly that term. So, integrate, you will get this. So, let me use a different color. So, you will get rho 1 power 1 minus n integral over db rho 1 of y u of x ds of x is, this is integral rho 1 to rho 2 is less than or equal to, so you will go that rho 2 power 1 minus n integral db rho 2. I am not doing anything special, just integrating with respect to and applying the limits, you see. So you have this inequality. This is true for any rho 1 and rho 2 such that rho 1 is less than or equal to rho 2 and with this it is between r and r. Now I can do two things. So what do I do is that so you look at the left hand side. So look at the left hand side. I want to make it a volume, it is equal to 1 by, I will multiply by n omega n on both sides. If I multiply by n omega n, rho 1 power n 1 minus n of anything n minus 1 and db rho 1, okay, and this is nothing but the average now, okay, of u of x ds of x. And then you have seen this average yesterday. Whenever you have some average around a neighborhood, and if that neighborhood shrinks and if u is continuous, it will go to its boundary value. So this will go to u of y because the ball of radius y, you see, as rho 1 tends to 0, as rho rho 1 tends to 0. So you got your, you look at here. So you got your left hand side. On the left hand side here, this converges to u of y and you take rho 2 equal to r to get the result. Okay. So you take rho 2 equal to r to get the first inequality, Okay. So let me go back to the inequality. Where is the inequality? Yeah, this is the first inequality, you see. This is your first inequality, right? This is your first inequality. Now I want to prove the second inequality. Only I have to prove result 1. The rest of our result is immediate. So we will go to this first inequality. Okay. Again, take rho such that 0 less than or equal to rho less than or equal to r. That implies this inequality uy, it is true for any r, in particular for any r. So rho 2 you took r, but you can take rho 2 equal to rho. So you get u of y is less than or equal to 1 by dbr db rho integral of db rho of y u of x ds of x. Okay. So I know how to evaluate this. Yesterday we again in the previous lecture, if you want to discuss an integral, if you want to get an volume integral, what you do is that you take integral, surface integrals about all balls. This is again we have to think and then integrate, and that is what we are going to do. So you take this to the left hand side db rho. So once you take it to the left side, what you will get is that n, this implies you take this db rho. So you get n omega n rho power n minus 1 u of y is less than or equal to integral over db rho of y u of x ds of x. Now integrate rho with respect to rho from 0 to r, the right hand side will become nothing but, if you integrate, that is nothing but your b r of y. That is how you get it. If you want to integrate the volume integral, you integrate over all the surfaces and integrate with respect to that radius of it dx. On the right hand side, what you get is, you will get n omega n, and you integrate this with respect to u of y, you exactly get rho power n by n, and that is r power n, that is nothing but the volume. So, the left hand side will be rho power n by n, n and n cancels, you get omega n into rho power n, r power n, because you are integrating rho from 0 to r. So, you exactly get your b r of y and u of y. So, if you, this completes the proof. So, if you take that modulus of b r of x on the right side, you get your inequality, volume inequality. So, that is a proof of it. Okay. And second thing, if u is superharmonic, if u is superharmonic, that implies minus u is subharmonic. Okay. And then apply the previous inequality. Then apply previous inequality. Okay. To get 3 follows from 1 and 2. Follows from 1 and 2. Okay. So, that is the thing we want to. So, you have the result. So, let me recall once again for your thing. So, whenever u is subharmonic, uy is less than or equal to either the surface average or the volume average. And if it is a harmonic, then it is the surface equal to the surface average or the volume average. And that ball, it can be in anything. So, that is what you have to see. It does not matter. Any ball you can average it out. The more interesting result is the converse to it. Converse to mean value property. Okay. Converse to mean value property. So, let me state the mean value property here. So, let me make some remark, maybe remark after stating the theorem, and then I will continue it in the next class. So, let me make a remark first. One remark. There are other remarks which I will make them. If you follow the proof implies that proof gives the following result. Just think about it. Gives the following result. Nothing to do, you just look at the proof, you will see this fact. If integral of du by d nu ds equal to 0 over the boundary equal to 0 for all b contained in omega, all balls contained in omega, that implies u is harmonic or u satisfies mean value property. Okay. You see. So, you can check when, so if you check your these averages, not even average, this quantity for all balls, then you can check that u satisfies the mean value property. That is all we have used it. We have used this is positive, you derive the inequality. If it is negative, you will derive the other inequality, and you follow that. So, let me state the theorem, and which we will prove in the next class. Theorem converse to mean value property, and then we will continue in the next class. Let u belongs to C2 of omega satisfy ux equal to, this is called the mean value property, 1 by the boundary of integral over b u of ds boundary is the same as, this is the mean value property, b integral over b u dx, this is the mean value property. That means for a function, twice differentiable function satisfies the mean value property, then u is harmonic. This is the converse. Earlier we have proved that if u is harmonic, then it satisfies the mean value property. So let me make a comment now which we may not prove here, remarks, and then remarks. So this converse implies in some sense mean value property is equivalent to harmonicity. That is a crucial thing. If it is harmonic, it is mean value property satisfied. Conversely, if u is twice differentiable and mean value property is satisfied, then Laplacian of that u is equal to 0. In other words, u is harmonic. The second remark is another interesting thing. If you observe the mean value property does not require that, though in the theorem I have added that, does not require u is in C2. U is continuous, is enough to define mean value, is continuous, is enough to satisfy, enough to define mean value property. So you see, the mean value property can be defined even without having its smoothness. So the question is that, what can you say about if the mean value property is satisfied this thing? In fact, this is a very interesting thing. If we get time, we may prove this. In fact, if mean value so starting, in fact, starting with a c omega function, starting with a continuous function, you define, assume, this is a more general theorem, okay, assume u satisfies mean value property. So you are not given the smoothness. Of course, in the theorem we are given the smoothness, but what I am saying is that even without the smoothness of C2 smoothness, continuity, you can define the mean value property. What this stronger theorem tells you, that then u is actually C infinity. So you do not need to start with a smooth function to define the mean value property. You can just start with a continuous function, then that continuous function, if the mean value property satisfy, that gives you u is C infinity in fact. In particular, it is C2 and hence it satisfies the harmonicity. So to prove this without this result, you maybe will indicate some other result later, but then you can also prove using the convolutions and mollifiers and all that, which I will not do that one. It is given in the reference of our book. So those who are interested should see this proof based on the mollifiers and convolutions. So I will stop here. So we will continue the proof of this converse to mean value theorem. Thank you.